Assalamu alaikum. In this video, I will explain multivariate version of the chain rules. In the case of univariate functions, suppose we have a function from domain A to B and another function from domain B to C. Let's call it G. Then we can compose these functions from A to C. We write like G after F. And this is defined as, so suppose x is an element of A, this is defined as g of f of x. So this is a composite function. And if f and g are both differentiable, we can define the derivative of this composite function, and that is the chain rule, remember? And so if we differentiate this composite function, g of f of x, what we have is this, g prime of f of x times f prime of x. So this is called the chain rule. So how can we extend this idea to multivariate functions? So let's start. First, we consider the following case. Suppose we have two univariate functions that are phi of t and psi of t. Then suppose we have a bivariate function, f of x and y. Then we can compose these functions. Okay, so f of phi of t and psi of t. So this is a composite function of f and phi and psi, and as a whole, this is a univariate function of t. Okay, so what we want to find is this derivative, dt f of phi of t and psi of t. So what does it look like? The answer is, first we differentiate f with respect to x. That means this first variable, okay? And evaluate that derivative at phi of t and psi of t. And then multiply that by the ordinary derivative of phi with respect to t. And this is a derivative, it's a function of t, and plus then partial derivative of f with respect to y. Y means this second argument, and evaluate at phi of t and psi of t. And multiply, I need to close this bracket, multiply that with the ordinary derivative, d psi dt of t. So this is the chain rule when these functions inside inner functions are univariate functions. Okay, let's make this statement more formal. So suppose we have a function f of xy that is totally differentiable. On an open region U, which is of course a subset of the two-dimensional plane, and we have x equal to phi of t and y equal to psi of t. These are differentiable functions. These are univariate functions and differentiable on an open interval. I. Okay, and suppose these points defined by this parametric function, parametric curve, phi of t and psi of t, if this point belongs to that open region U for all t in the interval I. So this is the interval on which phi and psi are defined. So if this is the case, then let's define the function z f of phi of t and psi of t. So this is a function defined on the same interval I as phi and psi. Then the derivative of this function, so dz dt or df dt of phi of t, psi of t is this. Just like we have written here, is this. So partial derivative first. Psi of t times d phi dt plus partial derivative with respect to y times d psi dt of t. So this is the chain rule. Maybe it's easier to see what's going on if we write this way. So the derivative of z with respect to t is its a derivative is a function of t, and partial derivative of z with respect to x, xy, times d phi dt at t. And this z dy partial derivative xy, and not partial, it's ordinary derivative d psi dt at t. Or even simpler, we may write dz dt is dz dx dx dt, and our phi is x, as we have defined here. X is equal to phi of t, y is equal to psi of t. So this is dz dy dy dt. So maybe it's easier to memorize this way. Okay, let's prove the chain rule of this version. Proof. First, we pick any element from the interval I. Okay, and let that element be t0, and let x0 be phi of t0 and y0 be psi of t0. And for any delta such that t0 plus delta is still in the interval. So let's say we have this open interval. We pick t0 and take small enough delta. It can be positive or negative. So let's say in this case it's positive. So this is delta. So this is t0 plus delta. So pick any delta so that t0 plus delta is still in the interval I. Then let's say h of delta be phi of t0 plus delta minus phi of t0, and k of delta be psi of t0 plus delta minus psi of t0. Okay, so if we define this way, then we take the limit in which delta goes to 0. So limit delta goes to 0, h of delta divided by delta. This is the definition of the derivative of phi. So this is d phi and dt at t0. And similarly, if we take the limit, delta going to 0, k of delta divided by delta is the derivative of the function psi, d psi dt of t0. This is just the definition of derivatives. Now, by assumption, f of xy is totally differentiable. Okay, since f of xy is totally differentiable, this is by assumption. Where is the assumption? We assume that f of xy is totally differentiable, right? On an open region U. So what this means is that we can have the following asymptotic expansion. Okay, that's right. F x0 plus h and y0 plus h is equal to f of x0 y0 plus partial derivative of f with respect to x at x0 y0 times x0 plus h minus x0 is h, and partial derivative of f with respect to y x0 y0, and wait a minute, it's not h, it's k, times k, plus little o of square root of h squared plus k squared. Okay, let's correct this one. By the way, h and k are, where is it? Here. H and k are defined in this way, right? And phi of t0 plus delta is defined to be, so phi of t0 is defined to be x0, psi of t0 is defined to be y0. So this plus h is this, phi of t0 plus delta, okay? So this one means phi of t0 plus delta, okay? This one, so y0 plus k means psi of t0 plus delta by the definitions of h and k. Okay, and little o and the distance from the origin of h and k, or distance between this point and this point. Okay, so this is what it means to be, for this function to be totally differentiable. Okay, so now we take delta to 0. Okay, then as delta goes to 0, we have little o square root of h squared plus k squared over delta is equal to, let's see, h over delta, little o h squared k squared, and divide. So we divide by h and multiply by h, and this will converge to 0. So h over delta converges to the derivative of phi, and that's what we have derived here, this one. this converges to this, and this part, since the numerator is little o, this will converge faster than converge to 0 faster than h. So this will converge to 0. So this is, let's see, maybe I should write, instead of equal, I should write converges to this, 0. So therefore, if we divide, if we move this, if we move this term to the left and divide everything by delta, we have the following. So f of x0 plus h, y0 plus k minus f of x0, y0 divided by delta equals to this one, partial derivative y0 h over delta k over delta. Wait a minute, did I write k? Yes. And plus little o, square root of h squared plus k squared over delta. Now we move delta to 0. Then this will disappear, and this part will converge to d psi dt at t0, and this term will converge to d phi dt t0, and the left hand side will converge to df dt at x0 y0. That is, of course, x0 y0 are phi of t0 and psi of t0 respectively. We have this. So this will, let's say, this will converge to 0. So therefore, we have df dt phi of this and partial derivative and the derivative phi. Zero and d psi dt at t0, and we are done. Let's see a simple example. Suppose we have z equals to f of xy, where f is any totally differentiable function, and let's say x is given by at plus b and y is given by ct plus d. So of course a, b, c, d, they are constants and t is a variable. Okay, if in this case the derivative dz dt is given by this. So first we differentiate, partially differentiate with respect to x, and differentiate x with respect to t, dx dt, then plus partially differentiate z with respect to y and differentiate y with respect to t. So this one, dz dx becomes just fx of xy, and this becomes, so if we differentiate this one with respect to t, we have a, and this one, partial derivative, that's fy of xy, and if we differentiate this with respect to t, we have c. So just tidy up a little bit. We have this. So a t plus b, c t plus d plus c fy a t plus b, c t plus d. Here it is. Next, we study a little bit more complicated version of the chain rule. So in this case, we have a function as usual, f of x and y, that is assumed to be totally differentiable. And x is now given as a function of two variables, u and v. And similarly, y is given as a function of two variables, u and v again. Then we compose these functions to have f of phi of u and v and psi of u and v. Now what we want to do is to find the derivative of this composite function f with respect to u or with respect to v. Okay, and this is given by this. This is actually easy to guess. So first we partially differentiate with respect to x, then differentiate x with respect to u, plus partially differentiate f with respect to y, and then differentiate y with respect to u. Okay, so this u is this u. So we just replace this one. Previously it was t, but just, and it was ordinary derivatives, but we just changed to partial derivatives and use these one of these variables u. And the same applies to the partial derivative with respect to v, and that is this. And f dy dv. Of course, this y is a function psi of u and v, and this x is the function phi of u and v. Okay, I will just omit the proof of this because it's quite easy. Just go back to the definition of partial derivatives. So first we fix one of the variables. Let's say we fix the value of v to some constant, then differentiate with respect to u. And for that we can apply the chain rule we have just proved for this univariate case. Okay. Then we can move v again, consider this as a function of v again, then it just becomes partial derivative, and do the same thing for the second one, and we are done. And let's see an example of such partial derivatives. Let's say we have f of xy, function of x and y, exponential of x squared plus y squared. And let's say phi of u and v be u cosine v, and psi u v be u sine v. So these are actually the polar coordinates of u and v. Okay, so v is the angle from the horizontal axis, and u is the distance from the origin. Right? And so we can define the composite. Let's define that as g of u and v. So that is f of phi of u and v, and psi of u and v. Okay, so if we calculate x squared plus y squared, so that is x squared plus y squared is phi squared plus psi squared, so that is u cos v squared plus u sine v squared. That is u squared plus cosine squared v sine squared v, and this is 1. So this is just u squared. Okay, so if we substitute this, then we have e to the power of this, that is u squared. So this is the composite function. And it is, as you can see, there is no v here. Okay, so it is trivial. Okay, but let's do the differentiation with respect to u first. Okay, so this is just differentiate this one with respect to u. Okay, so first we differentiate f with respect to x, and differentiate x with respect to u, and do this for y. Okay, so just blindly apply the chain rule. Let's see what happens. So if you differentiate this one with respect to x, what you have is, let's see, so this is e to the power of x squared plus something, so that's 2x e to the power of 2, e to the power of x squared plus y squared. And then you differentiate x, that is this one, with respect to u. This one with respect to u, so you have cosine v. Okay, and this one you have 2y e x squared plus y squared, and you differentiate this one with respect to u, you have sine v. Okay, and so, but x is this, so that's 2u cosine v exponential of u squared times cosine v, and 2 sine v exponential of u squared sine v. So we have cosine v, sine v, sine v, and u, and wait a minute, I forgot u here. Okay, so we have 2u e to the power of u squared, and cosine squared v plus sine squared v. And so this one is just 1, so we have 2u exponential of u squared. Okay, but if you just differentiate this one with respect to u, then you have the same thing here. See? Okay, then next differentiate this with respect to v, and you can expect that the result should be 0. But let's apply the chain rule blindly to see what happens. And this one. Okay, so this one we already calculated before. That's 2x. And this one, x, if you differentiate this one with respect to v, you have, let's see, u times negative sine v plus 2y, and if you differentiate this one with respect to v, you have u cosine v. Okay, now look at this. U times sine v is, so this part is negative y, right? So u sine v is y. So this is negative y, and u cosine v is x. Okay, so we have 2x, y exponential with negative sign and 2xy exponential. So this is 0. And you can get the same result just by differentiating this function with respect to v. You get the same result. And that's it for today. See you later.